Hey, okay. Hi. We're going to get into Unit 6. Unit 6 is thermochemistry. So we'll see a lot of stuff about heat, all right, and energy. All right. So let's share our screen, okay? This first video is something that you've already been introduced to. It's simply topic 6.1, and it is endothermic and exothermic reactions. All right, so I'll add a little bit to it. And endothermic and exothermic processes is actually what it's called. Endo versus exothermic. Processes. Okay, what do we know? We know that if we have a positive delta H, it's endothermic, and we know that heat has entered the system, okay? We're gonna have to talk about that a little bit. All right, what is the system? The system is whatever it is you're studying, all right? It could be the chemical reaction. It could be a physical change, all right? The system is what is under investigation. All right. We cannot directly measure the system. We can't get into the bonds breaking and forming, if you will. But so what we have here is we have the system, which is what we are concerned with, all right? And around it, we have the surroundings, all right? So you want to, when we talk about thermochem, definitely think about it in this way, okay? All right. So in an endothermic reaction, right, heat has left the surroundings and entered the system. Energy has. And we will experience that energy in the form of heat by way of temperature changes, all right? Such that the system, we already said, has gained energy, right? Right? Therefore, potential energy of products, right? And you know all this is greater than reactants. We could look at that on an energy profile, which should be very familiar to you at this point. Reactants, endothermic products, right? The difference between the energy of the reactants and the products is equal to the delta H, right? Potential energy products minus potential energy reactants. And in this case, it will be positive because it's endothermic. Now, if energy is going into the system and it is leaving the surroundings are losing energy. And how will we experience that? What will we observe? What will we observe? We will observe a decrease in the temperature. Okay? All right? So, all right. Okay. Endothermic, a process that is endothermic is breaking bonds. Breaking bonds is always an endothermic process. Right? You must add energy to overcome those forces of attraction. All right? Right? Going from solids to liquids to gases, always an endothermic process. Right? Right. What is the energy doing? Overcoming IMFs, those intermolecular forces. All right? Okay. All right. So we could also have our exothermic, right? Let's see. We would have a negative delta H. I like to keep things synonymous. Okay. Heat has exited the system. Such that the reactants, the products, I'm going to start to say in terms of products, have less potential energy than the reactants, right? Okay. So if we look at our system, which is whatever we are studying, listen to me, it could be the dissolving of a salt, could be the system. The system could be the melting of the ice, the freezing of the water. Oops, let's not draw through that. And then remember that the surroundings is everything else. Please put in your head that we observe the surroundings, and then we can determine what's occurring. We take what we observe in the surroundings and then infer what must be happening with the system. In an exothermic, the energy leaves the system and enters the surroundings, okay? Such that we would observe an increase in the temperature. Increase in the temperature of the surroundings. All right, you would see an increase in the temperature of the surroundings. What time is it? Okay. If we looked at on a graph, a reaction energy profile, potential energy, reaction coordinate. What are we, exothermic? So the reactants would be here and the products would be here, right? Once again, the difference between energy here is equal to negative delta H, and it's the potential energy of the products minus the potential energy of the reactants. And that will give you that negative value, okay? Well, breaking bonds is always endothermic. Forming bonds is exothermic, right? It's always an exothermic process. Going from a gas to a liquid to a solid is an exothermic process. So the surroundings become warmer. Okay. Yeah, I'm sorry, I was thinking. And what you do is you are IMFs, you're kind of creating IMFs, right? IMFs are forming. IMFs are forming here. So if you want to think about it, you know, when you, if you look up here, right, in this endothermic process, the process of going from a liquid to a gas, this is evaporation, right? Well, what happens when you sweat, right? When you sweat, the liquid on your arms, right, turns into a gas and it evaporates, right? And in the process, this absorbs heat, right? Right? Well, where does the heat come from? Because the system is the liquid turning into the gas. The surroundings is your arm. okay? So the heat leaves your arm and goes into the system, and your arm cools down. All right? Does that kind of make sense to you? Over here, let's say that we are putting HCl in water, right? It's not a chemical reaction. It's making a solution. So the delta H solution of, say, HCl, right? If you want. The process of putting the HCl in the water, right? The dissociation and the forming of interparticle attractions, all right? Interparticle attractions. And think about this. These are favorable attractions. So what are they going to do? They're going to give off energy, right? This right here is the system. We cannot get into the system, all right? But what we can stick our thermometer in is the surroundings. And this is the solution. All right? And what we'll see is the temperature will increase because this is overall an exothermic process, and these favorable attractions cause energy to be released to where? To the surroundings, and you put your temperature in the beaker and it's warmer and it feels hot. Okay? Got to think about it like that. We're always measuring the temperature of the surroundings. Now, it's true that the heat lost is always equal to the heat gained. Maybe I should say energy, right? First law of thermodynamics is the law of conservation of energy, right? It's always conserved. It's the fundamental principle behind thermochemistry, thermodynamics. First law of thermodynamics, law of conservation of energy. Okay? Okay. So we conserve energy just like we conserve mass. And I think that probably will cover this for now. All right. See you guys.